In childhood, we feel we are immortal. We are not going to die at all. We are not aware of our life. We think, why to worry? Why to hurry? We remain lazy. But as we grow up and reach towards the end of our life, we awake, arise, and try to finish our goals. But it is too late. Life is over, and in vain. It is everybody's experience that we get at the end. It is not clear that intelligence has any long term survival value. Hi guys, welcome again. Let us discuss some theories of Stephen Hawking. Black holes dissolving like aspirin. How Hawking changed physics. When Stephen Hawking postulated in the mid 1970s that black holes leak radiation, slowly dissolving like aspirin in a glass of water, he overturned a core tenet of the universe. Ever since Albert Einstein published his theory of general relativity in 1915, predicting the existence of black holes, it was thought they devour everything in their vicinity, including light. Black holes, it was thought, were bottomless pit from which matter and energy could never escape. But Hawking, sometimes described as the most influential theoretical physicist since Einstein, questioned this, saying that black holes were not really black at all and must emit particles. In doing so, he touched on a persistent headache for physicists. In doing so, he touched on a persistent headache for physicists. Einstein's theory, which has withstood every experimental test so far, does not explain the behavior of particles in the subatomic quantum sphere, considered controversial at first. Hawking's black hole theory pointed to a possible bridge between the two mainstay physics theories, general relativity and quantum mechanics. Hawking realized that black holes, those objects that are made of gravity, because of quantum mechanics, can actually emit particles. Astrophysicist Patrick Sutton of Cardiff University told AFP, "This was the first case where we had a physical process that links gravity, this classical theory of gravity, with quantum mechanics." The mechanism was named Hawking radiation, after the famous scientist who died Wednesday, Einstein's birthday, and it painted a completely new portrait of black holes. Stephen Hawking discovered that when the quantum laws governing the physics of atoms and elementary particles were applied to black holes, the surprising outcome was that black holes actually must emit radiation. Physicist Raymond Olcott of the University of Melbourne said via the Australian Science Media Centre. Second, theory of everything. Hawking showed that because black holes give off radiation, they actually have a temperature, and in losing mass and energy, they would slowly shrink and eventually evaporate. A real shock proposition according to Sutton. Hawking's most important scientific legacy is his idea Black holes slowly dissolve like aspirin in a glass of water, said Lisa Harvey Smith of the University of New South Wales. But Hawking radiation in turn poses a new problem, the so-called black hole information paradox. If a black hole disappears, all the cosmological information from matter and energy that initially went into it will disappear too. But physics predicts that information can never be lost. Hawking himself had considered a wager on the point, having initially bet that black hole information will ultimately be lost. It is still the focus of theoretical interest, a topic of debate and controversy more than 40 years after his discovery, said British cosmologist Martin Rees. A former collaborator of Hawking, he added, once described the radiation theory as causing more sleepless nights among theoretical physicists than any paper in history. Hawking radiation has heavily influenced the ongoing quest for new physics, a theory of everything that can unify general relativity and quantum mechanics. Besides his deep imprints on theoretical physics, many credit Hawking's popularization of science, including through his cosmology named book A Brief History of Time, with motivating their own interests and careers. His impact on the public understanding of science is almost beyond measure, said Harvey Smith. Third, black holes gain new powers when they spin fast enough. General relativity is a profoundly complex mathematical theory, but its description of black holes is amazingly simple. A stable black hole can be described by just three properties: its mass, its electric charge, and its rotation or spin. Since black holes aren't likely have much charge, it really takes just two properties. If you know a black hole's mass and spin, you know all there is to know about the black hole. This property is often summarized as the no-hair theorem. Especially, the theorem asserts that once matter falls into black hole, the only characteristic that remains is mass. You could make a black hole out of a sun's worth of hydrogen. Chairs or those old copies of National Geographic from Grandma's attic, and there would be no difference. Mass is mass as far as general relativity is concerned. In every case, the event origin of black hole is perfectly smooth, with no extra features. As Jacob Bekenstein said, black holes have no hair. But with all its predictive power, general relativity has a problem with a quantum theory. This is particularly true with black holes. If the no-hair theorem is correct, the information within an object is destroyed when it crosses the event horizon. Quantum theory says that information can never be destroyed. So the valid theory of gravity is contradicted by the valid theory of the quanta. This leads to problems such as the firewall paradox, which can't decide whether an event horizon should be hot or cold. The temperature within a room is an example of a scalar field. Credit Lucas Vieira. Several theories have been proposed to solve this contradiction, often involving extension to relativity. The difference between standard relativity and these modified theories can only be seen in extreme situations, making them difficult to study observationally. A new paper in Physical Review later shows how they might be studied through the spin of a black hole. Many modified relative theories have an extra parameter not seen in the standard theory. Known as a massless scalar field, it allows Einstein's model to connect with quantum theory in a way that is not contradictory. In this new work, the team looked at how such a scalar field connects to the rotation of a black hole. They found that at low spins, a modified black hole is indistinguishable from the standard model, but at high rotations, the scalar field allows a black hole to have extra features. In other words, in these alternative models, rapidly rotating black holes can have hair. The hairy aspects of rotating black holes would only be seen near the event horizon itself, but they would also affect merging black holes. As the authors point out, future gravitational wave observations should be able to use rapidly rotating black holes to determine whether an alternative to general relativity is valid. Einstein's theory of general relativity has passed every observational challenge so far. It will likely break down in the most extreme environments of the universe. Studies such as this show how we might be able to discover the theory that comes next. So guys, let us stop here. The remaining part we will see in the next video, part 3. Please like it, share it and subscribe it. Thanks a lot.